Welcome! In this session, we will tackle problem number 1495, number of subsequences that satisfy the given sum condition. This is an exciting problem that challenges us to work with subsequences and constraints on sums. Let's dive in and explore how to solve it step by step. In this problem, you're given an array of integers called nums and a target integer. The goal is to determine how many non-empty subsequences of nums satisfy the condition where the sum of the smallest and largest elements in the subsequence is less than or equal to the target. The input includes the array nums, where its length can go up to 100,000, and each element is between 1 and 1 million. The target is also a single integer, ranging from 1 to 1 million. Since the result could be very large, you need to return the answer modulo 10 to the power of 9 plus 7. Now, a subsequence is any sequence that can be derived from the array by removing some or no elements, without changing the order of the remaining elements. For instance, in an array, 3, 5, 6, 3, 5, 6, and 3, 5, 6 are all valid subsequences. The output is the total count of valid subsequences that meet the condition, returned modulo 10 to the power of 9 plus 7. For example, suppose nums is 3, 5, 6, 7, and the target is 9. The output is 4 because there are 4 subsequences that meet the condition. These are 3, where the minimum and maximum both equal 3, so their sum is 6, which is less than 9, 3, 5, where the minimum is 3 and the maximum is 5, giving a sum of 8, which is also less than 9, 3, 6, where the sum of the minimum and maximum is exactly 9, and 3, 5, 6, where the minimum is 3 and the maximum is 6, giving a sum of 9 as well. Any other subsequences either have a minimum and maximum sum greater than the target, or the subsequence is empty, which is not allowed. In another example, consider nums as 3, 3, 6, 8, and the target is 10. The output here is 6 because there are 6 valid subsequences. These include 3, and the other 3 separately, since each 3 forms a valid subsequence by itself. 3, 3, which includes both 3's, 3, 6, where the minimum is 3 and the maximum is 6, giving a sum of 9, 3, 3, 6, where the sum of the smallest and largest values is also 9, and 6, the single element subsequence where the minimum and maximum are both 6. Other subsequences, like 3, 8, exceed the target sum of 10, so they don't count. Now, let's look at a third example where nums is 2, 3, 4, 5, and the target is 8. Here, the output is 10. The valid subsequences include 2, where the minimum and maximum are both 2, making the sum 4, 2, 3, where the sum is 5, 2, 4, where the sum is 6, 2, 5, where the sum is 7, and 2, 3, 4, where the smallest value is 2 and the largest is 4, giving a sum of 6. These subsequences satisfy the condition of the minimum and maximum sum being less than or equal to 8. Additionally, there are other subsequences like 2, 3, 5, where the smallest value is 2 and the largest is 5, making the sum 7, 3, where the minimum and maximum are both 3, so the sum is 6, 3, 4, where the sum is 7, 3, 5, where the sum is 8, and 4, where the sum is just the single value 4. Any other subsequences, such as those including 5 as the smallest value, do not satisfy the condition because their sums exceed the target. To solve this problem efficiently, the constraints must be kept in mind. The array size can be as large as 100,000, and brute force approaches won't work for such large inputs. Edge cases like single element arrays, all elements exceeding half the target, or handling duplicates must also be considered. To tackle this problem, we start by sorting the array nums. Sorting helps us efficiently work with subsequences. Then, we can use a two-pointer approach where one pointer, I, represents the smallest element in the subsequence, and the other pointer, j, represents the largest. If the sum of nums, I, and nums, j, is less than or equal to the target, we calculate the number of subsequences that can be formed between the indices I and j. This calculation uses pre-computed powers of 2, which represent the number of subsets that can be formed from a given range. If the condition isn't met, we simply decrement the j pointer to try a smaller maximum value. Throughout, modular arithmetic ensures that results remain within bounds, as the answer must be returned modulo 10 to the power of 9 plus 7. To approach this problem, we first consider the brute force method. This involves generating all possible non-empty subsequences of the given array, nums. For each subsequence, we calculate the minimum and maximum elements, check if their sum satisfies the given condition, and count the valid ones. While this idea is intuitive and straightforward, it becomes computationally expensive very quickly. The number of subsequences grows exponentially as 2n, and for each subsequence, we need additional computation to verify the condition. This results in a time complexity of O2 to the power of n asterisk k, where k represents the cost of verifying each subsequence. With larger input sizes, this approach is impractical due to the sheer number of computations required. To handle this, we need a more efficient strategy, which leads us to explore an optimized approach using the two-pointer technique. The optimized approach builds on the observation that sorting the array simplifies the problem significantly. When the array is sorted, the smallest and largest elements of any subsequence correspond to specific indices. This allows us to determine their sum without generating the subsequences explicitly. Here's how it works. First, we sort the array nums. Then, we use two pointers, left starting at the beginning and right at the end of the array. For each nums, left, we look for the largest nums, right, such that their sum is less than or equal to the target. If the condition is satisfied, the number of valid subsequences that use nums, left, as the smallest element is 2 right left, since all subsets of elements between left and right are valid. If the condition holds, we increment left to explore the next smallest element. If it doesn't, we decrement right to narrow the range. To manage large results, modular arithmetic with 10⁻9 plus 7 is used. This method combines sorting, which has a complexity of O(n log n), with a two-pointer traversal of O(n), resulting in an overall time complexity of O(n log n). This approach is built on a few key observations. First, sorting makes the problem much easier to manage because the minimum and maximum elements in any range are predictable. Second, the two-pointer technique avoids explicitly generating subsequences, which drastically reduces the time complexity from exponential to logarithmic. Third, we can compute the number of valid subsequences in a range efficiently using powers of 2, leveraging the mathematical properties of subsets. Comparing our strategies, the brute force approach becomes infeasible for larger inputs due to its exponential complexity, while the two-pointer method is far more efficient and simpler to implement. Alternative methods, like dynamic programming or combinatorics, might also be considered, but the two-pointer approach is particularly well suited for this problem due to its clarity and efficiency. Ultimately, the two-pointer strategy stands out as the chosen method because it achieves an optimal balance of time complexity at O(n log n), simplicity in implementation, and practical application to the problem's constraints. Let's start by breaking down the problem. We're given an array nums and a target value target, and the goal is to count all non-empty subsequences where the sum of the minimum and maximum elements is less than or equal to the target. To solve this, the first step is generating all possible subsequences. Remember, a subsequence is any subset of elements from the array that maintains their original order, but the elements don't need to be contiguous. For an array of size n, there are 2n possible subsequences, including the empty one. To generate these, we can use a brute force method. This involves iterating through numbers from 1 to 2n1, where each number serves as a bit mask. Each bit in the bit mask represents whether to include the corresponding element from the array in the current subsequence. Once the subsequences are generated, the next task is to calculate the minimum and maximum values for each one. This requires traversing the elements in each subsequence and identifying the smallest and largest values. While this seems manageable, keep in mind that the computational cost of this step grows with the size of the subsequences, making it O(k) for a subsequence of size k. Now that we have the subsequences and their minimum and maximum values, the next step is to validate each subsequence against the given condition. Specifically, we check if the sum of the minimum and maximum values is less than or equal to the target. If this condition is met, the subsequence is valid, otherwise, it's not. For every valid subsequence, we increment a counter to keep track of how many such subsequences we find. At the end of this process, the counter will hold the total number of valid subsequences, which is the result we need to return. However, there are a few key insights to note about this process. First, the approach has exponential complexity because generating all subsequences requires O(2 to the power of n) time. This quickly becomes impractical for larger values of n, such as n greater than 20. Additionally, the need to compute the minimum and maximum for each subsequence adds further inefficiency, as it involves extra traversal. One thing to keep in mind is that we exclude empty subsequences from the count because the problem specifies that only non-empty subsequences should be considered. To implement this brute force approach, we rely on a few basic data structures. The input array nums is used to store the elements, and a simple counter variable is maintained to track the number of valid subsequences. While generating and evaluating subsequences, we use a temporary list to hold the elements of the current subsequence. Key operations in this approach include bit masking to efficiently represent whether each element is included or excluded from a subsequence, and a simple arithmetic comparison to validate whether min plus max satisfies the condition. While this method is straightforward, it's not optimal. Potential optimizations include sorting the array, which can significantly speed up validation by making the minimum and maximum elements more accessible. Another advanced technique is the two-pointer strategy, which avoids the need to explicitly generate subsequences. Instead, it directly counts valid ones by leveraging the properties of the sorted array. These optimizations can reduce the time complexity significantly. Speaking of complexity, the brute force approach has a time complexity of O(2 to the power of n asterisk k, where k is the average size of the subsequences, and a space complexity of O(k) for storing temporary subsequences during evaluation. This solution efficiently computes the number of subsequences that satisfy the given sum condition using a combination of sorting, two-pointer approach, and modular arithmetic. Here's a detailed breakdown. 1. Sorting the input. The array nums is sorted to ensure that smaller elements are on the left, and larger elements are on the right. This sorting facilitates the two-pointer approach to efficiently find valid subsequences. 2. Pre-compute powers of 2. The number of subsequences of a set of size k is 2(k). To avoid recomputing powers of 2 repeatedly and to handle modular arithmetic efficiently, an array powers is pre-computed. Each entry in powers is the value of 2(i% mod 4i from 0 to n1. 3. Two-pointer technique. Using two pointers, left starts at the beginning of the array, and right starts at the end. This allows us to evaluate the smallest and largest elements of potential subsequences efficiently. 4. Condition check. Nums, left, plus nums, right, equals target. If the sum of the smallest, nums, left, and largest, nums, right, elements is less than or equal to the target, then all subsequences formed by elements between left and right, inclusive, are valid. The count of such subsequences is 2(right left, which is retrieved from the pre-computed powers array. The result is updated modulo mod to prevent overflow. 5. Adjust pointers. If the condition is satisfied, left is increment to consider the next smallest element. Otherwise, right is decrement to reduce the largest element and try to satisfy the condition. 6. Output the result. The loop continues until left surpasses right, ensuring all possible subsequences are evaluated. Finally, the result is returned modulo 10(9 plus 7). This approach is efficient with a time complexity of O(n log n) due to sorting, and the two-pointer traversal is O(n). The use of modular arithmetic ensures the solution works for large input sizes without overflow. Here, we begin by importing the necessary libraries and defining our solution class. The method number subsec is where the logic resides. First, we define a constant mod to handle large numbers, as required by the problem constraints. Then, we sort the input array nums in ascending order to simplify the process of finding valid subsequences. Next, we pre-compute the powers of 2 modulo mod, storing them in an array called powers. This pre-computation ensures that we can quickly determine the number of subsequences for any given range later on. The powers array is initialized with 1 at index 0, and each subsequent value is calculated by multiplying the previous one by 2 and taking the modulo. Following this setup, we initialize 2 pointers, left and right, to the start and end of the array, respectively, and a variable result to accumulate the count of valid subsequences. The while loop begins, and the idea is to use the 2 pointers to evaluate the smallest and largest elements in the current range of the array. If the sum of nums, left, and nums, right, is less than or equal to the target, it means that all subsequences formed by including nums, left, and any combination of elements between the left and right pointers are valid. To account for these, we add the pre-computed value of powers, right left, to the result, ensuring the sum stays within bounds using modulo mod. After this, we increment the left pointer to evaluate the next smallest element. However, if the sum of nums, left, and nums, right, exceeds the target, we need to reduce the maximum value in the range by decrementing the right pointer. This adjustment helps narrow the search space to find valid subsequences. The loop continues until the two pointers meet, and finally, we return the accumulated result as the total count of subsequences that satisfy the given condition. To solve this problem, we start by setting up the input and preparing some essential data. The input array is nums equals 3, 5, 6, 7, and the target is 9. First, we sort the array, although in this case, it's already sorted as 3, 5, 6, 7. Next, we pre-compute the powers of 2 modulo 10 to the power of 9 plus 7, giving us the array powers equals 1, 2, 4, 8. This will help us efficiently calculate the count of subsequences later. We also initialize 2 pointers, left at the start of the array, index 0, and right at the end, index 3, along with a result variable set to 0. In the first iteration, we calculate the sum of nums, left, and nums, right, which is 3 plus 7 is equal to 10. Since this exceeds the target, we reduce the range by decrementing the right pointer to 2. In the second iteration, the sum becomes 3 plus 6 is equal to 9, which meets the condition. We then add the count of valid subsequences starting with nums, left, using powers, right left, which is powers, 2 to 0, equals 4. Finally, we move the left pointer forward to index 1, narrowing the range further. Now, in the third iteration, with left at index 1 and right at index 2, we calculate the sum nums, left, plus nums, right, equals 5 plus 6 is equal to 11, which exceeds the target. To reduce the sum, we decrement the right pointer to index 1. In the fourth iteration, the sum becomes nums, left, plus nums, right, equals 5 plus 5 is equal to 10, which still exceeds the target. Again, we decrement the right pointer, this time to index 0. At this point, the left pointer is greater than the right pointer, so we exit the loop. The final result, stored in the result variable, is 4, which represents the count of valid subsequences that satisfy the given condition. For the second example, nums equals 2, 3, 4, 5, and the target is 7. We begin by sorting the array, which remains 2, 3, 4, 5. The pre-computed powers of 2 are the same as before, powers equals 1, 2, 4, 8. We initialize left at index 0, right at index 3, and result at 0. In the first iteration, the sum of nums, left, and nums, right, is 2 plus 5 is equal to 7, which is within the target. We add the count of valid subsequences using powers, right left, which is powers, 3 to 0, equals 8. Then, we increment the left pointer to index 1. In the second iteration, the sum becomes nums, left, plus nums, right, equals 3 plus 5 is equal to 8, which exceeds the target. To reduce the maximum value, we decrement the right pointer to index 2. In the third iteration, with left at index 1 and right at index 2, the sum of nums, left, plus nums, right, is 3 plus 4 is equal to 7, which satisfies the target. We add the count of valid subsequences using powers, right left, which is powers, 2 to 1, equals 2. After this, we increment the left pointer to index 2. In the fourth iteration, the sum becomes nums, left, plus nums, right, equals 4 plus 4 is equal to 8, which exceeds the target. We decrement the right pointer to index 1. At this point, the left pointer is greater than the right pointer, so we exit the loop. The final result, stored in the result variable, is 10, which is the total number of valid subsequences for this example. In the third example, nums equals 1, 2, 3, 4, and the target is 5. After sorting, the array remains 1, 2, 3, 4. We pre-compute the same powers of 2, powers equals 1, 2, 4, 8. As before, we initialize left at index 0, right at index 3, and result at 0. In the first iteration, the sum nums, left, plus nums, right, is 1 plus 4 is equal to 5, which is within the target. We add the count of subsequences using powers, right left, which is powers, 3 to 0, equals 8. Then, we increment the left pointer to index 1. In the second iteration, the sum becomes nums, left, plus nums, right, equals 2 plus 4 is equal to 6, which exceeds the target. To reduce the sum, we decrement the right pointer to index 2. In the third iteration, with left at index 1 and right at index 2, the sum nums, left, plus nums, right, is 2 plus 3 is equal to 5, which meets the target. We add the count of valid subsequences using powers, right, left, which is powers, 2 to 1 equals 2. Then, we increment the left pointer to index 2. In the fourth iteration, the sum becomes nums, left, plus nums, right, equals 3 plus 3 is equal to 6, which exceeds the target. We decrement the right pointer to index 1. At this point, the left pointer is greater than the right pointer, so we exit the loop. The final result is 10, representing the total number of valid subsequences for this example. To analyze the time complexity of our solution, let's break it into three main components. First, sorting the input array nums. Since sorting is performed using an efficient algorithm like quicksort or merge sort, it takes n*log n time, where n is the length of the array. This step is the most computationally expensive and dominates the pre-processing stage. Next, we pre-compute the powers of 2 up to n elements. This involves a simple loop over the array, making it an O(n) operation. Finally, the two-pointer traversal of the array is carried out. Here, the left pointer starts at the beginning of the array, while the right pointer starts at the end. During the traversal, either the left pointer increments or the right pointer decrements, and since both pointers move at most n steps in total, this step is also O(n). These three steps form the foundation of our time complexity analysis. When we combine all the components, the dominant term is the sorting step, which is O(n*log n). The other steps, such as pre-computing powers and performing the two-pointer traversal, are linear at O(n) each and are asymptotically smaller. Therefore, the overall time complexity of our approach is O(n*log n). Now turning to space complexity, the solution requires storing the input array nums, which takes O(n) space. Additionally, we use an auxiliary array called powers to store the pre-computed powers of 2 modulo 10 to the power of 9 plus 7, which also requires O(n) space. The rest of the variables, such as left, right, result, and others, are constants, consuming O(1) space. These components together make up the memory usage of the solution. When we combine the space requirements, the storage for the input array and the auxiliary powers array dominate, both requiring O(n) space. Therefore, the total space complexity of the solution is O(n). As for the time complexity across different scenarios, the sorting step determines the overall complexity, and since sorting is performed regardless of the input characteristics, the time complexity remains O(n*log n for the best, average, and worst cases. The additional steps, like the two-pointer traversal and power pre-computation, are linear and unaffected by input variations. This consistency in asymptotic behavior ensures that our approach is robust across all cases. To highlight the efficiency of our solution, let's compare it with the brute force approach. A brute force method would require generating all possible subsequences of the array and checking whether each satisfies the given condition. With an array of size n, there are 2 to the power of n possible subsequences, leading to a time complexity of O(2 to the power of n, which becomes infeasible for larger inputs. In contrast, our optimized approach reduces the complexity dramatically by sorting the array and using a two-pointer technique, achieving O(n*log n time complexity. This is exponentially faster as n increases. Additionally, the brute force approach would require substantial space to store all subsequences, while our optimized solution only requires O(n) space for the input array and auxiliary computations. By breaking down the steps, we see that the sorting step dominates at O(n*log n, with linear contributions from pre-computing powers and the two-pointer traversal. This efficient combination of time and space usage makes our solution highly suitable for competitive programming and large-scale inputs. When tackling this problem, there are several common pitfalls to be aware of. First, failing to handle edge cases like arrays with only one element or arrays where all elements are identical can lead to incorrect results or runtime errors, especially when calculating minimum and maximum values. This is a fundamental issue that can be avoided with careful boundary checks. Next, attempting a brute force approach on large input sizes is another mistake. Generating all possible subsequences for an array of size n results in an exponential time complexity of 2 to the power of n, which is simply impractical for larger values of n, such as n greater than 20. It's crucial to recognize when such approaches are infeasible. Another frequent error occurs in sliding window implementations, where developers might forget to shrink the window when the condition is no longer satisfied. This oversight can lead to either overcounting invalid subsequences or missing valid ones altogether. Mismanaging boundary conditions is also a common source of bugs. For instance, off-by-one errors when iterating through a range can cause out-of-bound errors or result in skipping valid subsequences. Finally, in languages with fixed integer sizes like C++, overlooking integer overflow during intermediate calculations, such as summing the minimum and maximum values, can produce incorrect results. Being mindful of these mistakes in testing edge cases thoroughly will help mitigate these risks. To excel in interviews, it's important to focus on key strategies. Recognizing patterns in array problems is one of the most valuable skills. Many problems involving subsequences or subarrays can be optimized using techniques like sliding windows, monotonic queues, or dynamic programming. Identifying the underlying pattern early on can guide you toward the most efficient solution. It's also helpful to start by briefly discussing a brute force approach. This clarifies your thought process and provides a baseline, but you should quickly transition to optimizing the solution. For example, you might aim to reduce exponential time complexity, such as 2 to the power of n, to something more efficient like n log n, or n. Additionally, explicitly discussing edge cases during interviews is a great habit to demonstrate thoroughness. Highlight how your solution handles scenarios such as empty arrays, very large inputs, or constraints on values. Finally, be prepared to discuss trade-offs between time and space complexity. For instance, using auxiliary data structures like heaps or queues can improve time efficiency but may require additional memory. Explaining these trade-offs shows that you understand the broader implications of your approach. There are several related problems on LeetCode that can help you practice similar techniques. For example, problem 862, which involves finding the shortest subarray with a sum at least k, uses a sliding window approach. Problem 209, minimum size subarray sum, also relies on the two-pointer technique to optimize subarray calculations. Problem 239, sliding window maximum, demonstrates how a monotonic queue can efficiently handle dynamic window computations. Lastly, problem 78, subsets, focuses on generating all subsequences using backtracking, which can deepen your understanding of combinatorial problems. In addition to these, alternative approaches to the given problem can be explored. One efficient method is the sliding window approach, where two pointers are used to maintain a valid window while ensuring the condition on the minimum and maximum values is satisfied. This method balances efficiency and simplicity but requires careful attention to shrinking the window correctly. Another option is using a monotonic queue to dynamically track the minimum or maximum within the window. This approach is faster than sorting at each step, achieving n time complexity, but it does require additional space for maintaining the deque. For more advanced scenarios, data structures like segment trees or binary index trees can be used to handle range queries efficiently. While these are powerful tools, they come with increased implementation complexity and potential space overhead. Choosing the right approach depends on the specific constraints and requirements of the problem at hand. Great job! We reviewed the solution for problem number 1495 and covered efficient techniques like sorting and the two-pointer method. These strategies are invaluable for solving similar problems. Thanks for tuning in. Remember to like, subscribe, and keep practicing. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!